Okay. Comes pretty quick. All right, so we're gonna work on this example today. That notice one thing. This is the problem where you have the issue with the so-called settlement. Okay, if you can recall, this is the example from last time. You know, it's the same one. This very one, yeah, the same. But this time, before the loading occurs, you know, before we assign the load to the beam itself, prior to loading, that means before the loading, okay? Before the loading, the beam experiences the settlement as follows. So at support A, it comes down here, even before the loading, for 1.25 centimeters, okay? Support B comes down for 0.3 centimeter. Oops, I'm sorry, just put on the wrong support. So let's begin again, my bad. Okay, support A should be this one. That's right. Support A here. Ooh. This one, sorry, comes down 1.25 centimeter. Support B comes down 0.3. And support C comes down, crazy number, 0.53 centimeter. So the significant thing that occurs here is that you have the joint movement. Okay, and when you have the joint movement, that means you are going to have to deal with the moment due to joint displacement. But not only that, at support A, you know, which is this one, that is B, that is C, we also have the counterclockwise rotation. Okay, equals 9 multiplied by 10 to the power of minus 4 radian. Okay, that means generally support A, which you already know, it's a fixed support. And when you know it's a fixed support, some students may still be confused about the fixed support. Fixed support is the only location that you know that rotation is 0, right? So generally theta A is 0. In general, because it's fixed, it's the only location we know how much rotation is going to be. In this case, you have the prescribed rotation, and that is theta A is equal to, because it's counterclockwise, minus 9 multiplied by 10,000 radian. Okay, so this is not 0, but it's something that you know. So it's not an unknown. Okay, and one more thing that you should understand is that when you have this settlement, generally 1.25 is greater than 0.3, right? So I can say that my structure will come down at A much more than at B. Okay, you guys can see that, right? And at C, it comes down a little bit more than at B. So the fact that A comes down more than B means that your member is now oriented like this, right? So you can actually see that your member is what? Rotates the entire member. Now we are not talking about joint rotation, okay? We are talking about the rotation of the member itself. The rotation of the member occurs because your joint A and B move. So this is the rotation of the member, rotation of member. See, rotation of member, not the joint, caused by joint displacement. Okay, when your joint displaces, your member will rotate, and this means it will lead to the psi term in our equation. Okay, any question? Now let's come back here and you will see. Okay, let me draw the BC first. Because this is 0.3 and this is 0.53, so BC will be oriented a little bit like this. Okay, now you can clearly see that member AB is rotating counterclockwise, while member BC is now rotating clockwise. And again, let me remind you that I don't know why C is gone, so let me put it back again. C. Let me remind you again that for slope deflection, we use clockwise positive. Okay, so when you have the counterclockwise psi term, that your psi must be negative, and here your psi must be positive. You see, what we have here is not rocket science. It's just a simple, investigation of how your member rotates. So it would be extremely sad if you cannot get it right. Notice one more thing about this beam, that is, we don't have any fixed end moment, because fixed end moment is caused by the external load. In this case, we don't have any load, so we don't have any fixed end moment. All right, so let's do our job and try to determine our psi. Now you have theta A equal to this already. You have the distance, and therefore you can calculate the psi, which is equal to delta over L, remember? Now, member AB, in your equation, you will have MAB and MBA, right? But the psi is always the same because it's the rotation of your member, so you can have only one psi per one member. Now you can calculate your psi AB. You can always, maybe if you're not sure about yourself, whether or not you could deal with the sign convention, you can always use, let's say, if this is node 1, that is node 2, you can always use, y2 minus y1 and y3 minus y2 to calculate your delta, right? So in this case, it is 0.3 minus 1.25 over the length of 3 meters. But be careful, your displacement is in centimeter, so you better use the centimeter unit for the length as well. So this clearly gives us the negative sign, and that is equal to minus 0.0032 radian. Okay, and likewise we can do the same with psi B, C. And you can use, y3 minus y2, just like, simple calculation of the slope. Or you can just look at your member and determine right away that it is positive because it is clockwise. So it is 0.53 minus 0.3 over the length of 500 centimeters. So this is 0.00046 radian. Okay, so we got pretty much everything we want, And remember, this is the same O beam from the previous example. So I don't need to repeat all those steps, but you perhaps want me to do it. So let's do it quickly. Step 0, determine the unknowns. So we have theta B and theta C as your unknown. So it's 2 unknowns. Okay. Step number 1 is a relative stiffness. So we have, say, KAB is 2K from last time, right? And KBC is 3K. That's all business. Step number 2 is fixed end moment. So you can say no, because we don't have load just yet. So that means we can move on and start writing our slope deflection equation right away. Okay, it's the equations. This time, MAB then. It's 2E, 2K, okay. 2 theta A, so that's 2, and then theta A is that number, okay, minus 9 multiplied by 10,000, or it is 0.0009 radian. Remember, it is counterclockwise, so it is negative. Plus theta B minus 3 psi. Remember your formula? Our formula has been developed based on the sign convention that our member rotates clockwise, so we have the counterclockwise moment as a result. So this is the negative term, and then you have the negative sign, so it's minus 3 multiplied by minus 0.0032. Okay, no fixed end moment. So we can just wrap up our MAB right away. It is equal to 4E K theta B, that's my 4. And then plus 0.0312 E K. So you see, even without the load, we have the joint displacement. We have the our moment. Next is MBA. Again, it's 2E, 2K. Now it becomes 2 theta B plus theta A, right? So it's 2 theta B plus theta A, which is minus 0.0009 radian, minus 3 psi, which is the same. By now you should realize that when you have joint displacement, the result of joint displacement will give you, equal moment on both ends of the member. Okay. The next, okay, let's wrap this up. So it's 8 EK theta B plus 0.0348 EK. Next stop is MBC. MBC is now 2E, 3K. Okay. Now we have both 2 theta B plus theta C, again minus 3 psi. Psi this time is positive of 0.00046. radian. This gives us 12 ek theta b plus 6 ek theta c minus 0.0082 ek. Okay, the last one is MCB. So I think it's business as usual. 2E, 3K. Don't forget to use the correct stiffness now, guys. 2 theta C plus theta B minus the same thing. Okay, so when wrapping MCB up, I will begin my equation with theta B so that I have theta B aligned in the first position. So when I construct my equilibrium equation, it is easier and I would become less susceptible in making mistake. All right, so let's say MCB, it's going to be 6 ek theta b plus 12 ek theta c minus, that should not be a surprise at all. It's the same number, 0.0828 ek. Okay, so now we got our slope deflection equation. We can go on to the next step and create our equilibrium equation. Okay, now you have MAB plus I'm sorry, it's supposed to be MBA, right? Yeah, just sleepwalking a little bit. So it's MBA plus MBZ equal to 0. What do we have here? That's 8 and 12. See how easy that is? So it becomes 20, and then you have 6. Okay, and then that the later term. So from that, oh, it just, okay, right there, we can see it. So 8 and 12, so that's 20 ek theta b plus 6 ek theta c, and then that term. Let me play some calculation music, and then I have 0.0265 ek equal to 0. Now you guys, even though we have the cantilever portion, but when you look back at this cantilever has no load. So basically you can say that, you know, this thing doesn't exist. It doesn't exist without the load, right? So you can just forget about it. So this is equivalent to having just what we call a simple end support, where you know that the moment here at C must be 0. So we can just say sigma mc equal to 0, which means, oops, go again. Which means MCB itself must be 0, okay? I forgot to write this down, but you guys should know that this equation is sigma MB equal to 0, right? So the next one is sigma MZ equal to 0, which means that MC itself, MCB is 0. So we have that. So put B together, 6 ek theta B plus 12 ek theta C, and then minus that term, 0.00828 ek equal to 0. All right, so we have 2 equations and 2 unknowns. which means we can solve this. And before that, again, as usual, just take a look at the coefficient that you have. See, that's 6, that's 6. So again, it's symmetric. So we are good to go. And after solving this, I got zeta B is equal to should be EK zeta B, right? No, just zeta B. That's equal to minus 0.0018, and zeta C is 0.0016. Okay. So I have given you some numbers so that you can calculate the end results. Given this, that's the Young's modulus of steel and the moment of inertia of 40,000. That's a large section. So if we have this, we can calculate moment due to settlement. Okay. All right. Now, so we can back here and calculate our end moments. So MAB, again, back to that equation, but you need to substitute everything correctly because in fact it's done in terms of EK as well. You know, we use K, and here E is 2 million, and I is 4 multiplied by 10 to the power of 4 divided by I cannot find where I got this, so please hang on a minute. I need to go back to check my relative stiffness for a moment. Okay. Because we use our K equal to I over 6, right? So that's a 2K, and our K is I over 6, and we have 2K, so therefore that cancels out. And we have I over 6, and we need to change the unit a little bit, so we'll multiply that by 100 squared. And then we have the results, this, and then zeta B 0.0018 plus the psi term 0.312. Okay, that's MAB equals, it's pretty big, 32,000 kilogram meter. Now you see, just one example, it shows you that the moment at A or MAB is rather large, even though your structure has settlement only 1 centimeter. 1 centimeter is just like this much, you know. Wow, how can we have so much moment? It's because we have the structure with a large I, so you know it takes a lot to move that structure. Okay, and likewise you get MBA in the same fashion, and it is 27 kilogram meter. All right, and MBC, it's roughly the same, minus 27, but I got the number round off a little bit, so it's not exactly the same, but you should know that in fact these two numbers should come out identical. Otherwise, your sigma MB would not be 0. Okay, and that's it. It's a round off of a number, and then MCB, well, of course, should come out to be 0. Okay. Now, if I put this back on, now I have this. That's step number 5. Did I? Okay. So step number 6. In reactions. Okay. Now I can write down my free body diagram. I have the positive value here, which means it's clockwise moment on AB. Let me change the unit so that I can write less 32 ton-meter. That is also clockwise 27 ton-meter. And for member BC, MC 0, and then this one is negative, so it counterclockwise. 27 ton-meter, so to speak. And from this, I can calculate my shear force. Okay, so one of them, this one, the left one is the reaction, but this is not the reaction, it's a shear, right? It's on the left of the support B. And this is simply 27 plus 32 divided by the length of the member. So how much? 3 meters, right? And then this is down, so this is up. So that is 27 over 5 meters. Okay. So you see, if I am going to complete the shear force and the bending moment diagram, we have the negative shear. And then that, oops, gotta have a couple here, right? And then your bending moment diagram, remember that when in slope deflection, clockwise is positive, but when you want to write your bending moment diagram, it's back to the same sign convention. So that is positive moment, 32. This one becomes negative, minus 27. And then that's negative 27, and it goes to 0. Okay, so this becomes your bending moment diagram. It's BMD. That's a shear force diagram. Now, the fact that I want to draw the bending moment diagram here is because I want to show you that generally, when you have a structure like this, you know, under the typical load, moment at A should be negative. And likewise, moment at B, because I did not complete this one, right? So let me try to complete the one from the previous time so that you can see, okay, just to save time. Okay, so from this, you know, the previous problem, you guys can pick up the old one. Hello, is that okay? From this one, again, you can just, because this is 2 to 1, right? Yeah. Okay. This is the beam with the load. So that's 2 meters and that's 1 meter. So in fact, you can calculate the shear caused by the load 9 tons. So this is 6, right? Perhaps. Yeah, that's 6, because I can just 18 multiply 9 multiplied by 2 divided by 3, so that's 6. That's 3. This is the shear caused by 9 tons, and then this is the total of the moment is clockwise, so you're gonna have this. and that, right? And this shear is 4.94 minus 1.53, oops, divided by 3. And this is exactly the same, but in opposite direction. You could just take moment of the entire member, or you could just do this, okay? And in the end, what we have here is 7.14 tons for this reaction. And here we have 1.86. And you could do the same with this. That is 2.4 with a 5-meter span. So the reaction due to the gravity load is half by each, and then you have the this time this one is up, right? Because 4.94 is greater than 3, and that one is down, and this term is 4.94 minus 3 divided by 5. This term is, of course, 2.4 multiplied by 5 over 2. Okay, you can just do that. And you have here is 6.39. Here is 5.61. And here is so straightforward, right? It's 2. So from here, you see your shear force diagram. Oh, it's so ugly. Let me draw it again. Okay, the shear force diagram is gonna go like that's downward, right? Oh no, so this is upward. That's a downward due to the couple, but this is upward. That is upward, that is up, and that is up. Okay, so we have shear force diagram. That's 1.86. Come down till you see the point low, and it drops down to minus 7.14, right? You run into the reaction, and here goes up to the shear on the left, which is 6.39. It comes down to shear on the right, which is 5.61. It goes up to meet that point load, which is 2. So that's your shear force diagram, and your bending moment diagram is going to look like this. So generally, when you have a fixed support, it's normally the negative moment. That's 1.53 minus 1.53, and the end moment here, you know, you should get this, right? That's a negative moment of 4.94. So that one, you can put it right away on your structure. And that is minus how much? 3, right? Here is minus 3. So it's just a matter of filling in the middle, you know. See if this will give you the positive value or not. And in this case, it does. So this is how your bending moment diagram is going to look like. And this is large enough to give you positive moment as well. So that's your bending moment diagram. Notice that generally at the support, you will always have the negative moment, right? Because we have discussed about this before, that when you have the structure and you want to load it, chances are you cannot have it bend any other way. It has to bend in the negative shape only. But whether or not it can have the positive curvature like this depends on the span length and the load. And in this case, it does. So let me, you know what? Change the color a little bit. In this case, oh no, forgot. So now it turns green, everything. Fine. I can use red, I suppose. That's a positive moment that you can have because the span is long and the load is heavy. And here again, at the fixed support, generally you have the negative moment because under gravity load, there is no other way that it can be bent. But if it's long enough and the load is heavy, you can have your positive curvature. So this kind of behavior you can perhaps see from the beam right away, and therefore you can sort of anticipate the result that is going to happen. But for the now what? But for this one, you know, because the settlement, it caused your moment to be sort of opposite. See, instead of having the negative moment at the support this time, you have positive, for example. So in generally, what I want to tell you is that when you are dealing with the settlement problem, generally moment becomes the opposite. So the settlement is the most unwanted problem because it happens underneath with your foundation. You don't know what's happening down there. And when it happens, the moment that you expect to occur will be in the opposite direction. And you now taking the RC class, you will learn that, you know, you put your reinforcement where the tension is in RC, right? Because concrete cannot take compression. So you generally put the reinforcement where tension is. And now because generally, if you have a continuous beam like this, you would expect your moment to be negative at the support like this, and negative at the support, negative, and positive at midspan. But when the settlement occurs, everything turns upside down. So all your reinforcement will become useless under settlement. So that is why we don't like settlement at all, and we try to prevent it not to happen. Okay, now one more thing before we end this session is this. Please pay attention to what we are doing, what we have done with example number 6. This problem in particular, you guys are given the movement of the joint. Okay, so in other words, you know how much each joint in your structure displaces. But the problem will become a little bit more sour when, say, you are dealing with the frame. Because frame is a problem that is pretty much similar to the problem that we just did, except that when we push this to the side, this joint will move, correct, under the lateral load. So your member here will, you know, displace like this. So most definitely, this member will have the side, which can be calculated. That is also the side, right? Which can be calculated from the formula that we wrote before. It's delta over L. Now L, you know, correct? You know how long your column is going to be. But the problem is this. It will become your unknown, and therefore you're going to have one extra unknown coming from the joint displacement of the structure in the frame problem. Okay, and we shall see that maybe next week. Okay, from now on we have another issue we need to take care of. So yeah, without any question, we can have a break now. So is there any question?
Teacher,
Yeah.
may I ask how come we have the theta at the fixed support?
This, you mean this picture?
No, the previous example.
Oh, you mean the example? I see. Well, we try to fix it, but settlement occurs, so your structure is damaged. That's why the support rotates a little bit, but still it's a fixed value. So yeah, you name it a fix. You hope that your rotation is 0, but you know it's the same because this is your support, right? And you expect your displacement to be 0 here as well. But then this aster strikes, you have settlement at the support, and then you have rotation at the fix. Correct?
Yes.
But you don't doubt why you have the settlement at the support. It's supposed to be 0 too, right?
Yes.
Yeah. So it happens. So this is the case where, you know, you build your structure and then, wow, something wrong happens. And then, you know, there's a displacement of your structure. There's a settlement of your support, and your support also rotates. So with this equation, we can sort of calculate how much force, how much internal force is induced in your structure by this sort of movement.
Oh, okay. Okay.
Yeah. All right. So, any question? Any more?
Teacher,
Yeah.
how the relative stiffness come? I confused when I see the previous one.
You mean since the previous example?
Yes.
Okay. We use the least common number. In Thai, we call it kun rom noi, right? So let's come back here. Since the very first one. So let's say the stiffness of member AB here is I over 3, right? It's I over length. Length is 3 meters and moment of inertia is I. So that's I over 3 for KAB, correct? And then K for member BC, the length is 5, but you have 2.5 I. So the stiffness of member BC is 2.5 I over 5 or I over 2. So now, if you want to use the relative stiffness, it means that you are comparing these two stiffnesses. Now, how do you compare them? You just find the least common number between 3 and 2, that is 6, right? It's the least common number for 3 and 2, 6. So I say I call K equal to I over 6. So KAB, which is I over 3, if I say K is equal to I over 6, KAB is equal to 2K, right? Because my K is equal to I over 6, so multiplied by 2, it becomes I over 3 or KAB. And because K is equal to I over 6, when I multiply by 3, it becomes I over 2, which is KBC. So by multiplying the stiffness of your members with the least common number, you can see better how each one is stronger than the other. Which one is stronger than the other. Okay? You don't have to do this. You can go ahead and use I over 3 and I over 2. It doesn't harm anyone to use the direct stiffness like this. It may harm your pride a little bit that you cannot calculate your least common number. That's all. If it doesn't hurt, go ahead and use I over L. If it does hurt and doesn't look cool, use relative stiffness. Okay, this is not mandatory. I can give you the example. Say, you know, if you have, say, beam. Let's make it maybe 3 span. Okay, let's say it's all L. All right, but somehow this one is I and this one is 6I. That's one is I. So when you compare I over L, it's pretty obvious, right? That the first one, this is I over L, then this is 6I over L. So you can say the span in the middle is 6K, 6 times stronger than the one at the ends, correct? That's pretty straightforward. That's I, not some crazy looking thing, okay? But when you begin to have maybe a more complicated issue, maybe like this, short and then long and then long and then short. And then let's say this is 6I, I, and then this is L, this is 2L, this is 3L, for example. You can say, you know, I'm not going to write down A, B, C, D, but, you know, naturally you should assume that this is member A, B, B, C, C, D, and D, E, right? So K, A, B in this case, it just I over 2L. You can go ahead and use that, you know, it doesn't hurt. KBC is 6I over 3L or 2I over L. So you can see perhaps that BC is stronger than AB when you compare I over L or stiffness, but you may want to make your life easier. So you say, okay, this is, I'm going to use I over 2 is equal to K. So this becomes K. This becomes 4K. You can work, you can work easier, but you don't have to, you know. Because it really saddens me when students try to use relative stiffness and then mess it up. Because this is simple math, you know. But it is absolutely important that you realize that the stiffness matters. And we account for that with the I over L term. Right? Right? You don't have to, but you can. But if you want to, you must get it correct. Because if you mess up 3 things from the beginning, you're done for. First is the unknowns. If you identify the unknowns incorrectly, you're done, 0. Second, you identify the load incorrectly. That comes in terms of the fixed end moment. That means you're solving a different beam. You're not solving the beam that you're supposed to solve. That's 0. That's fatal. Okay. And third, stiffness. If you mess it up, you're solving the different structure. Okay. So that's why this is the level, the preliminary level in our rubric. If you don't get these levels right, the rest of your work is garbage. And I don't know how to, you know, mildly put it, but, you know, as an engineer, you don't even recognize your own structure. And that comes down to the word that you guys are familiar with, fatal, right? Fatal. Any more questions, folks?
Teacher.
Yep.
Since we can find the internal load, right, from the settlement.
Yeah, I would say internal force.
Or internal force.
Yes.
So we can find the settlement from the soil mechanic too in
Yes,
the
that's right.
structural
That's right.
design.
That's right. You can find the settlement from the calculation based on soil mechanics. You can just take your survey equipment out and measure it.
So for the structural design, we have to design for the settlement too.
You know, I know where you're getting at, and I like your question very much. In design, we don't design for settlement because we hope that it doesn't occur. Okay.
Okay.
So there will be an art when you construct your foundation. You need to make sure that all the settlement occur before you start doing something on it. So in soil mechanics, I don't know if it is taught in soil mechanics. I remember vaguely that there would be a short-term displacement and a long-term displacement, correct?
Yeah.
The short-term is larger, but it happens quickly at the beginning. And
Yes.
then long-term is only minimal and it happens on a very, very long span of time. Okay, and we don't want it on our structure, especially short-term. And I brought this problem up because there's so many things to talk about and so many things that you should know as engineers. Okay, so now it's 10:30. I don't know if I should continue to talk about this or I should give you a break first. Let's give it a break because otherwise the video will get to be too long, and I'll come back and I will give you a little bit more of, a settlement problem. Okay.
Okay.
Okay, good. So I think you should have a break now. So I'm gonna stop the sharing. Okay, and I am back in the main page and I am, oh, Shanatip, that's how you look like right now. Okay, so I'm gonna stop the recording.